Welcome back to the deep dive. Today we're jumping into a really foundational piece of physics, Chapter 20 of Feynman's Lectures, Vol.2. It's called Solutions of Maxwell's Equations in Free Space. Our goal here is, well, it's kind of like physics alchemy. We want to pull out the big ideas, the concepts that show how light emerges from these equations. And we'll try to do it without, staring endlessly at the dense math.
Yeah, exactly. And this chapter, it's really the culmination of classical E&M. We've built up Maxwell's equations, right, based on charges and currents. Now we ask, okay, what if there are no charges, no currents? So Math BFJ 20 just say empty space, free space.
Yeah.
What do the fields do then if you just leave them alone? If there's some disturbance, how does it behave?
That's a great setup. So the sources are gone, but maybe some fields are still, out there. Before we get to the big mathematical proof, what's the first picture Feynman gives us, the sort of tangible example to help us visualize these moving fields?
He starts with probably the simplest thing you could imagine that creates a propagating field, an infinite sheet of current. Imagine a huge flat sheet carrying current, and it just suddenly switches on.
Okay, an infinitely large wall of moving charge.
Yeah.
Very physics.
Right, a theoretical construct, but useful. The main takeaway from this sheet example is the idea of a wavefront. See, the electric and magnetic fields, math BFE and math BFB, they don't just pop up everywhere instantly when you flip the switch at, say, time 0. They actually travel outward from that sheet at a specific finite speed. We call it sidily. So if you're standing some distance 6 miles away, the fields are just 0, nothing, until time equals 6 decibel. Then, bam, the wavefront hits you.
Ah, okay. So that totally changes how we think about cause and effect in fields. The field I measure here right now isn't caused by what the source is doing now. It's based on what the source did earlier.
Precisely. That's the concept of retarded time. The field E all out at distance EC cells at time actually depends on the current D dollar back at the source at an earlier time, target dollar. And that earlier time is the E dollar minus the travel time, CC cells time. The field carries a kind of memory. If the current in that sheet suddenly turned off, you wouldn't know it instantly. You'd have to wait for that off signal, that new wavefront, to reach you traveling at $1.
And this simple picture, it also naturally leads to superposition, doesn't it? Which is just fundamental for waves. Like if the current sheet turns on, then off, then maybe on again, we don't need a whole new complicated solution.
Exactly. You just calculate the field for on, the field for off, starting a bit later, and then the field for on again. You just add them up.
Yeah.
Victorially, of course. Solve the simple case, and you can build up the complex ones. So that current sheet, it gives us the physical intuition. Disturbances travel, and they travel at a finite speed.
Okay, that example makes sense. But the real power here is Maxwell's equations themselves, their universality. So moving to the next part, how do we show this propagation speed isn't just a feature of that specific sheet example? How does the math itself, the core equations, demand that these electromagnetic disturbances must travel as waves at speed c to dollar?
Well, it's actually remarkably elegant. You take Maxwell's equations, but the versions for free space, remember, math BFJ $,
Yeah.
and then you manipulate them mathematically. It involves looking at how the fields curl and change in space. It's also called taking the curl of the curl, standard vector calculus stuff. The goal is to get an equation that just has, say, the electric field math BFE in it and describes how it changes in space and time.
Okay, so you do these. Vector gymnastics, as Feynman might say. You rearrange the equations.
Yeah, and when the dust settles, what you end up with is something incredibly familiar to physicists. It's the three-dimensional wave equation, and it's the exact same mathematical form that describes how sound waves move through air, or ripples spread on a pond, or how a vibration travels down a guitar string. It tells us unequivocally that the electric field math BFD2 and actually the magnetic field math BFD2 must behave like waves. They have to oscillate and propagate.
So the laws originally just describing static forces and steady currents, they inherently contain wave behavior. That's amazing. But the real kicker, the absolute mic drop moment, is the speed that falls out of that equation, isn't it?
Oh, absolutely. The wave equation has a constant in it, which represents the square of the wave speed. And that constant turns out to be $1 epsilon. Now, just pause on that. Epsilon dollar, the permittivity of free space that comes from experiments with static charges, like Coulomb's law. It tells you how easy it is to make an electric field in vacuum. And the permeability of free space that comes from experiments with steady currents and magnetic fields, like Ampere's law. How easy it is to make a magnetic field.
Wait, so these are numbers you get from rubbing amber or measuring forces between wires, like really basic static tabletop experiments, nothing to do with light initially.
Exactly, just measurements of static electric and magnetic effects. And when Maxwell put those numbers, epsilon dollars, into his derived wave equation, The calculated speed, $1, came out to be about 300,000 kilometers per second.
Which was?
The known speed of light, $C.
Yeah.
Measured by astronomers and physicists completely independently.
Wow. Okay. So electromagnetism predicted its own speed, and it just was the speed of light. That's the unification. Electricity, magnetism, and light are all the same phenomena.
That's the moment. It's arguably the birth of modern physics. Light is an electromagnetic wave.
Let's drill down into the solution itself a bit. The simplest case is a wave just moving in one direction, say along the x-axis. The general solution looks like a piece E x s e t plus g x plus c t. Let's unpack that. What does that first term 5x ct physically mean?
Okay, so phi represents the shape of the wave. It could be anything, a sharp pulse, a smooth sine wave, some complex wiggle. It's just some function. The argument is the key. It means that whatever shape 5s you start with, it moves rigidly along the positive x-axis, unchanged. At speed, t-dols, if you look at it a little later, the whole shape is just shifted to the right. It doesn't spread out or change form in the simple 1D case. It just moves.
And the full solution says the total field is always just a combination of two such waves. One moving right, 5x xat, and one moving left, gx plus xt.
That's the most general possibility in one dimension, yes. A superposition of waves traveling in opposite directions. And crucially, when you dig into what math BFE and math BFB are doing inside these waves, you find another constraint. For these simple plane waves, the electric field vector math BFE, the magnetic field vector math BFB, and the direction the wave is traveling, they all have to be mutually perpendicular, at right angles to each other.
Okay, so if the wave is coming straight at me, the electric field might be oscillating vertically, up and down.
Then the magnetic field must be oscillating horizontally, side to side, and both are perpendicular to the direction of motion towards you.
That's why we call them transverse waves. The oscillation is transverse or perpendicular to the direction of energy travel.
Precisely. They're intrinsically linked. You can't have one without the other in a traveling wave.
And the energy flow. That's given by the vector cross product, math BFE times math BFD, which points, you guessed it, straight forward in the direction the wave is moving. The math also forces the magnitudes to be related, medial, CB always, for these waves in free space. This is still... It requires a huge amount of imagination, doesn't it? We're talking about invisible fields, waving at right angles, shooting through empty space at this incredible speed. Feynman himself talks about how hard this is to visualize properly. What's his advice when our everyday intuition just kind of breaks?
Yeah, he really emphasizes the sheer scale of imagination needed in physics. It's not like picturing billiard balls. He points out that to really picture the electromagnetic field, at every single point in space, you need to imagine 6 numbers. The 3 components of mass BFE2, XGX, AEC, and the 3 components of math BFPs, and the 3 components of math BFB, BXB, BRIA.
6 independent values at every point, and they're all changing in time according to Maxwell's equations.
So,
like, that's tough to hold in your head.
It really is. And that's why he sometimes uses analogies, like the famous one comparing the field to maybe an elastic solid, like a jello or jelly, that can be stretched or twisted by forces. But he's also very quick to warn against taking those analogies too literally. They're just crutches for our intuition. Ultimately, he says, you have to trust the mathematics. The rules, the laws embodied in the equations, that's the description of reality, even if it feels weird or abstract compared to our macroscopic world.
The equations define the game. And if you play by those rules, you get waves moving at $, you get the transverse nature, it's all baked in.
And that universality is why the same set of equations describes everything from the radio waves carrying this conversation potentially to the light you see by, the UV rays from the sun, X-rays, the whole electromagnetic spectrum. It's all just different frequency solutions to the same wave equation.
Okay, so we understand the basic wave behavior, especially the plane wave. But you mentioned earlier, plane waves are infinite. They're a simplification. Real sources like a light bulb filament or an antenna, or even just a single oscillating electron, they're localized in space. How do we model waves coming from a specific point source? We need to think spherically, right?
Exactly right. Plane waves are a good approximation if you're very far away from a source, where the wavefronts look almost flat. But near the source, the waves have to be spreading out in all directions, spherically.
Like ripples from a stone dropped in a pond, but in 3D.
Precisely. So we need to find solutions to the wave equation in spherical coordinates.
And what does that solution look like for a wave that's specifically moving outward from a source at the center?
Well, the general form for a spherical wave, let's call it θ, where the dollars is the distance from the origin, still involves that retarded time idea. It depends on the function $5 evaluated at t or die, but there's a crucial difference from the 1D case. The whole thing is divided by the distance, $. So the solution looks like PFTRCRL.
Okay, hang on. Why the dollar bastard? What's the physics behind the amplitude decreasing as you get further away?
Ah, that's a really neat point. It comes down to energy conservation. Think about the total energy the source is radiating per second. It's some fixed amount, right? Now, as that wave travels outward, that energy gets spread over the surface of an expanding sphere. What's the surface area of a sphere of radius dollars?
$4 pi R22.
Exactly. The area grows like 2. So
Yep.
if the total energy flowing through that surface is constant, the energy density, the energy per unit area must decrease as 122. It has to get diluted as it spreads out.
Okay, energy density falls as 122, and energy in a wave is usually proportional to the amplitude squared.
Bingo. If the energy density goes as 122, the amplitude of the wave itself must fall off as viriler. That Browner dependence is the signature of a wave expanding spherically in 3 dimensions from a localized source. It's physically necessary. And, by the way, there's technically another solution, dgt plus RCRE, which would represent waves converging inward towards the source. But physically, we usually discard that one because we assume waves are caused by sources and radiate outward.
That makes sense. It all fits together from the simple sheet to the general wave equation forced by Maxwell's laws to this realistic dollar-dollar fall-off for spherical waves. It feels very complete.
It really is. And Feynman shows that these spherical wave solutions also smoothly connect back to the static field cases, like the 102-hour force law for a static charge, when you consider the appropriate limits. It's a unified description.
So let's wrap this up. What's the big picture for you, the learner, listening to this? We started with Maxwell's compact, elegant equations describing electricity and magnetism, and we found that when you look at them in empty space, with no charges or currents, they don't just predict static fields, they demand the existence of electromagnetic waves traveling at a very specific speed. The speed of light wasn't put in, it came out of the fundamental properties of electric and magnetic fields in vacuum.
Yeah, and we pulled out, what, 3 main things? First, these disturbances travel at 2 SV, and they carry a memory of what the source was doing earlier, that retarded time concept. Second, these waves are transverse. Math BSB wiggle perpendicular to each other and perpendicular to the direction the wave is going. And third, for realistic localized sources, the waves spread out spherically, and their amplitude has to decrease as a dollar-dollar because of energy conservation.
Okay, so here's a final thought, something provocative for you to take away and maybe ponder. We found that the fields, Math BFE way, obey the wave equation, but Feynman also shows that the underlying potentials, the scalar potential field layer and the vector potential Math BFAs, they also satisfy the exact same wave equation in free space. Now, if the physics, the forces, the fields all depend on these potentials, and the potentials themselves are unified by this single wave behavior, does that maybe hint that the old classical separation between electric potential and magnetic potential isn't quite so fundamental when things are changing rapidly, when waves are involved? Could they be different aspects of a single propagating potential wave? Something to maybe explore on your own.
That's a great question. It definitely points towards deeper connections, maybe even relativistic formulations where theory and math BF are combined.
Definitely food for thought. Thank you for joining us on this deep dive into the fascinating world inside Maxwell's equations.